Say that we have the parabola x squared equals to 4ay. If I consider 2 points on the parabola, okay, let's say that this is going to be the point P and this is going to be the point Q. If I join the points P and Q together, then the resulting interval is known as a chord. Now, back when I was looking at parabola in trigonometry, we said that the equation of the chord joining 2 points on the parabola is relatively pointless because when we're looking at this in trigonometry, we essentially said that the point P is given by x1, y1, and the point Q is given by x2, y2. So naturally, if I just want to find the line joining x1, y1 with x2, y2, then the resulting equation is just the 2-point formula. Okay, so that's obviously fairly pointless. However, the story changes, okay, when we're looking at the parametric equation of the chord. So we know that the point P that lies on the parabola can be represented by the parametric equation x equals to 2ap, y is equals to ap squared, and the point Q can be represented by 2aq, comma, aq squared. So therefore, if I want to look for the equation of the chord PQ, we need to start off by checking out the gradient of the chord PQ. So the gradient of the chord PQ is therefore given by ap squared divided by aq squared, that's y2 minus y1, right? Divided by run, which is x2 minus x1, so that's going to be 2ap minus 2aq. So we can see that we can do a lot of simplification here. For example, I can factorize a out from the top. So I've got a lots of p squared minus q squared divided by, in the denominator, we've got 2a as a common factor. Alright, so I've got 2a outside of p minus q. And on top of this, what we should also realize is that p squared minus q squared is the difference of two squares. So by difference of two squares, we can factorize this further into a bracket p plus q times p minus q over 2a times p minus q. And here, we can see that the a's cancel from the top and bottom. And we can also cancel the p minus q from the top and bottom. And what's left for the gradient of pq is therefore just half brackets p plus q. So that's going to be the gradient of the chord pq. As soon as I've got the gradient of this chord, we know that it passes through p, okay, which is 2ap ap squared. So if I use this as x1, y1, then we know that the equation, right, of pq is going to be y minus y1, which I'm using as ap squared, is equal to the gradient, which we just found, to be half brackets p plus q, times x minus x1, which is 2ap. Okay, so that's what we have here. And of course, if I expand the whole lot, what we're looking at is y minus ap squared. And when I expand the right, I'm going to expand this by taking the half p plus q, right, as a whole and multiplying it with the x. And then I'm going to take the half p plus q, and then I'm going to multiply that with minus 2ap, right? What I don't want to do right now is expand term by term. So if I jot that down, we're looking at half p plus q lots of x, and then I've got half p plus q times minus 2ap. So that's going to be minus ap times p plus q, right? Because the half times 2 cancels away. So once I've got this, the reason why I want not to expand term by term is because I want the half p plus q in front of the x. However, with the ap times p plus q at the back, I do actually want to expand this because I'm actually going to gain a minus ap squared on the right, which is going to simplify with a minus ap squared on the left. So in other words, we're looking at y minus ap squared is equals to half p plus q lots of x. And then expanding this, I'm looking at minus ap squared minus apq. And we can see that we can cancel the minus ap squared from both sides. And what's left is the equation y is equals to half p plus q times x minus a times p times q. And this is the standard parametric equation of the chord. And of course, one remark about this equation is that you guys can't just memorize this equation and quote it whenever you want. What we need to do is obviously learn the proof. Okay, most of the times during the exam will actually get us to prove this. Okay, you guys will see this a lot. Of course, we'll actually be proving this so much, right, and so often that you guys will probably be able to memorize this result. But unless the question tells us otherwise, for example, the question could be like, you may assume that the equation of the chord PQ is given by this, okay, and then they go, oh, do not prove, okay, or alternatively, the question is worded as write down the equation of the chord PQ, okay, with the exception of those two. In all other scenarios, we need to see the proof. Okay, so make sure you guys know how to prove this particular equation. Okay, we count this as standard bookwork. Now that being said, one last thing which I want to point out with the chord PQ is that the chord PQ is just a random interval joining any 2 points, okay, on the parabola. And as such, we can draw infinitely many chords, okay, that join 2 random points on the parabola. Now, some of those chords are special in the sense that they might pass through the focus. So if the chord PQ passes through the focus, which is given by 0, A, then we call the chord PQ a focal chord. And when we have focal chords, we actually have a special condition when P times Q is equals to -1. Okay, and to show that, let's say that this is S0, A. So PQ is a focal chord, right? PQ is a focal chord if it passes through the focus, right? If it passes through S0, A, right? And what that implies for us is that if the focal chord passes through S0, A, then we can say, right? Remember that the equation of the chord is given by y is equals to half P plus Q times X minus APQ. So therefore, if it passes through the focus S0, A, I can take X for 0, Y for A, and substitute everything into the equation of the chord, and everything should work out fine. Okay, so in other words, I'm expecting Y equals to A to be equals to half P plus Q times 0 minus A times P times Q. Right, and the half P plus Q times 0, that's just going to be nothing. So in other words, we know that negative APQ is equals to A. And if I divide both sides by negative A, therefore P times Q is equals to -1. And that's the special condition that will always happen whenever the chord PQ passes through the focus S0, A. Now, one way to interpret this, okay, I know that interpretation is not necessary right now. It's more important when we get around to locus a little bit later. But what this is saying, okay, is that P, small p is the parameter that tells us pretty much where the point P is. And small q is telling us where the point Q is. So obviously, if I've got the chord PQ, P and Q have to move relative to each other. So if I fix P somewhere, Q has to be fixed at another point such that PQ passes through the focus, right? Q cannot wander around randomly. So the result of that is whatever P is, Q will have to reflect that value of P. So this is like a constraint, okay, that fixes Q to always be equals to -1 over P. That way, chord PQ will always pass through the focus. So if I move P up here, you guys can see that in order for the chord PQ to remain a focal chord, Q cannot be anywhere it wants to be. Q is now fixed at this point, right? If I move P further up, Q has to move closer, right? And vice versa, right? Of course, in that case, I'm saying that P is free to wander and Q has to move in turn with P. Okay, but of course, we can also say that Q is free to wander, right? And then P has to move relative to Q. So those two are pretty much talking about exactly the same thing. At the end of the day, it's a constraint that dictates how P and Q move relative to each other, such that the line joining them passes through the focus. Now that condition, okay, we don't need to interpret it so deeply right now. You guys just have to remember that we know that a chord is a focal chord if it passes through the focus S0, A, and we always have a special condition corresponding to that, and we'll use this a little bit later. Okay, so make sure you guys learn how to prove the equation of the chord, and this is what we have for parametric equation of the chord.